The mechanism of fatigue failure. The fatigue failure always begin at a crack. So this one is the part here which one is failed because of a fatigue failure, and we can visualize here a crack. Now this crack may be present in the material since its manufacture, or may have been developed over a time due to cyclic loading, as there is a cyclic straining and the stress concentration. So there are the three processes involved in the fatigue process. That is, the first is a crack initiation, then we have a crack propagation, and the third is the crack due to unstable crack growth. The first stage here is the crack initiation. This can be for a very short duration. Second stage, that is a crack propagation stage, involves most of the life of the part, and the third stage we have instantaneous. In the first case, that is a crack initiation, once a micro crack is established due to the stress concentration, and if the material is poor, then the crack will initiate, or the material is not manufactured as per the standard design, particularly the geometry, most of the crack initiated where we have a stress concentration. Say for example here we have a plate which is loaded, and we have nominal stress produced in a vertical direction, and if we have a elliptical hole, how to calculate the theoretical stress concentration factor is known to us. This value of a major axis will be taken as a dimension which is perpendicular to the load will be equal to A, and other dimension which is parallel to the load will be taken as B, that is a minor axis. In this case we can calculate the stress concentration factor, and we know the value of theoretical stress concentration factor is equal to 1 plus 2 times of a perpendicular dimension to the stress, that will be equal to A divided by B. And we know the value of Kt is same as equal to sigma maximum divided by the nominal stress. So maximum stress produced will be equal to 1 plus 2 times of A divided by B multiplied by nominal stress. Suppose we have very small thickness, that is the value of B is almost equal to 0. So this time the value of B will tend to 0. If B is tend to 0, you will get a crack of this type, and we have sigma maximum will be equal to 1 plus 2 times of A divided by B, which is equal to 0 of nominal stress. So theoretically we can say here the maximum stress will be equal to infinity. So for a sharp crack, B would approach to 0. In that case, the value of sigma max will tend to infinity, and therefore the part will fail. As far as the brittle material is considered, as compared to the ductile material, the brittle material are the materials that can fracture without yielding, but the brittle fracture is not instantaneous. Crack propagation needs a time, so we need a time here for the crack propagation. For that we require the energy to feed the crack, then only the crack will propagate. That is the one reason, that is the stress concentration is one reason. Second is the temperature also. So not only the brittle material fracture, most materials are ductile to brittle transition temperature, and when the temperature drops, then the crack initiate and the crack propagate only under the tensile loading. As the tensile loading shoot up, then the crack propagate. Crack propagate means crack will enlarge. Basically the crack is developed due to the tensile loading as well as shearing, and even in the case of plane shear. The crack propagation due to tensile is the most common phenomena in the fatigue process. So the mode 1 phenomena is representing the propagation due to tensile loading. We have a crack here, and because of the tensile stress that result in the opening the crack and the propagation of a crack. Crack can also propagate due to in-plane shear, that is the second mode. So in this case we have in-plane shear, that is this force which is acting on the top and the force acting at the bottom. They are parallel to each other. So this one is the second mode, is due to shear. The third mode of the crack propagation is due to again the shear, but this one is from the out of the plane. Out of the plane means that one force will act in this way, and we have second parallel force will act parallel to it but out of the plane. This one is in plane and this one is tension. This phenomena is more common in the fatigue failure. So fatigue failure is much more complicated phenomena than the static failure, where such complicated factors are involved. Also, the testing of material for fatigue property is more complicated and much more time consuming than the static testing. So basically there are the three modes. First mode is the tensile stress that result in the opening the crack and the crack propagation. Second is a sliding mode due to the in-plane shear, and the third is a tearing mode which results from the out of the plane shear. Out of the three modes that we have discussed here, the mode 1 is most common of crack propagation. The fatigue life methods are aimed to determine the life, that is the number of loading cycle for an element until its failure. In the static theory of failures, we have done already the tensile test and the torsion test. Both these tensile and the torsion test apply the loads which are slowly and once the specimen is loaded completely. That is a gradual loading and the load will be full after some time. These are the static tests and measure the static strengths like SYT, SYS, and while some machine parts may see only the static loads in their lifetime, most will see the loads and the stresses that vary in time, and the material will behave very differently in response to the loads that come and go, which is called as the fatigue load, than they do to loads that remain static. Most of the machine design deals with the design of a parts for time varying loads, so we need to know the fatigue strength of the materials under these conditions. There are the three major fatigue life methods where each is more accurate for some types of loading or some other materials. Three methods are present for the fatigue life. That is a stress life method, second is a strain life method, and the third the linear elastic fracture mechanics method. For calculation of a fatigue property of the material are obtained by using the standard rotating beam test. So this specimen is used to find out the fatigue property of the material. This test was carried out on a rotating beam and is called as RR Murray test. So we are using here highly polished circular section specimen and is subjected to cyclic loading. The beam is supported on the two extreme ends. So we have a load is acting on the specimen is equal to F. So this force is also equal to F. Since it's a symmetrical loading, so reaction on the support is also equal to F. So both the reactions will be equal to F. At center line we have minimum cross-sectional area, so bending moment will be maximum. We'll develop here the shear force diagram and the bending moment diagram. So we'll plot here the shear force on the y-axis. Initially here at the left support we have vertical load is acting upward, so we'll move vertically upward by distance equal to F. So this force is same as equal to F. From this point up to this load, the load is not acting, the shear force is remain constant. Then because of the force F, we have to move vertically downward. So let's move vertically downward and again you come equal to 0. From this force F to the other end force F, the load is remain constant, that equal to 0, that is the shear force is equal to 0. Again due to this shear force, you have to move vertically downward. Again there is no load acting, so shear force is remain constant, and finally we'll close with the shear force equal to F. So this figure represents the shear force diagram. And now we'll develop the bending moment diagram. The support, the bending moment will be equal to 0. Here the shear force is remain constant and it is a rectangle. So in the case of bending moment diagram, you will get a triangle and you will attain a value equal to M. In the shear force diagram, there is no change in the shear force. The bending moment diagram is remain constant. And again we have a negative rectangle, so we have to draw the negative slope and the bending moment will be equal to 0. So over the section here, we have a constant maximum bending moment, but the area is continuously changing, that the diameter is continuously changes. At the exactly at the center here, we have minimum diameter, and if the diameter is minimum, in that case we have maximum bending stress is produced. This maximum bending stress produced will be given by sigma b maximum equal to 32 times m divided by pi into dq. And since we have a continuous rotation, So the bending stress will be compression, alternately it become tension, again it become compression, again it become tension. So there is a continuous sign change of the stress produced on the top surface as bottom surface, which one is the case of a completely reverse loading. The minimum value will be same as equal to the maximum value, so sigma minimum will be same as equal to negative of sigma maximum. So stress will continuously change from 0 to maximum value, which one is the bending stress is given as 32 m by pi d cube. Again it will attain a value equal to 0 and then it becomes negative bending stress and the cycle will continue. So this peak value represent here the sigma max and this minimum value will be equal to sigma minimum. In the case of completely reverse loading, we have mean stress will be equal to 0 and therefore we have amplitude stress sigma A is same as equal to sigma max. So specimen is subjected to constant bending moment is rotated at a very high speed, due to which the fibers of the specimen except on the neutral axis undergo repeated stress reversals, that is a maximum tensile stress to maximum compressive stress. And this test is repeated for a number of similar specimens, subjecting them to different values of the stress and the number of stress reversal that specimen survives before the fracture are counted, and the data is plotted on log paper. So once the test is conducted, then you have to plot the data for a stress versus number of cycles, that is the life of a component, which one is also called as the number of stress cycle. The test specimen is subjected to completely reverse stress. So on y-axis we are plotting the amplitude stress, and for completely reverse stress this value is same as equal to sigma maximum. So on this axis we are plotting the value of sigma A, and on x-axis we are plotting the number of cycles, starting with 10 to the power 0 that equal to 1, then we have 10 to the power 1, 10 to the power 2, 10 to the power 3. Likewise we are having a life of component 10 to the power 4, 10 to the power 5, 10 to the power 6, 10 to the power 7 and 10 to the power 8. Supposed to be very large life, that is the infinite life of a component. Some data points you can record on the SN diagram will be initially for a low cycle you will get the failure points as like this one. Then from 10 to the power 3 to 10 to the power 6 the failure points will be observed, which are changes almost linearly, and after 10 to the power 6 again you will observe here is that we are getting some data points in this fashion. If the test was conducted for a different number of alternating cycles, we'll develop a plot that we called as SN diagram. It is also called as a stress life diagram. So this data I have plotted for steel. If the material will change, we will get a different points on the SN diagram. So the starting value was taken as SUT. Use the value of SUT, that is for one cycle. From 10 to the power 3 to 10 to the power 6, we almost guessed a straight line. At 10 to the power 6, there is a formation of a knee and you get a horizontal straight line. So this point formed here is called as knee point. So failure less than 10 to the power 3, that is 1000 cycle, is classified as low cycle fatigue. So this range represent here the low cycle fatigue range. And the failure with more than 1000 cycle is classified as high cycle fatigue. So from 10 to the power 3 onward we have a high cycle fatigue. For some materials that never fail for a stress level below a certain threshold, that is represented by this stress level, and this stress level is called as the endurance strength, which one is SE. So if you consider here any stress below the value of SE, then part will have a infinite life, and the corresponding threshold value is called as the endurance limit, and the stress below the endurance limit will guarantee that the part will have infinite life, that is 10 to the power 7, 10 to the power 8 will be treated as an infinite life. This is the case of a steel, so we are getting here the endurance strength, but in the same plot we are using for aluminium, as such knee formation will not be there. Since here we are using the two term, one is a infinite life, then other term we'll use as a finite life. So up to 10 to the power 7, if the component will survive, it will be called as the finite life. So from 1 cycle to 10 to the power 7 cycle, it will be called as a finite life. And there is an overlap between the finite life and infinite life. So infinite life means that if the component will survive from 10 to the power 6 onward, then it will be called as infinite line. So there is a slightly, this zone is overlap between the finite life to infinite life. So this diagram is called as SN diagram, or it is called as the Waller strength life diagram. Remember here we are plotting here the amplitude stress, and in the case of completely reverse stress, the amplitude stress is same as the maximum stress. So in this case we have a low cycle fatigue is from number of cycle equal to 1 to 1000. So for low cycle fatigue means that number of cycle is 1 less than n less than 1000. And for this low cycle we can ignore the fatigue effects, and since we have ignored the fatigue effect, the design is based on the static loading. So we can use here the static failure analysis. The high cycle fatigue means that the number of stress cycle n should exceed than 1000. That will be called as high cycle fatigue. A component has an infinite life if the number of the stress cycle will exceed than 10 to the power 6. So if the number of cycle n is greater than 10 to the power 6, it will be called as infinite life. The corresponding stress here will be AC, and AC is called as the endurance strength. And this value of AC, that is the endurance limit, is much lower as compared to SUT. So on y-axis we are plotting the fatigue strength, which is represented by SF. Is same as your amplitude stress, and for completely reverse stress, amplitude stress will be same as the maximum stress. So mainly we are interested here in an infinite life, and for a finite life we are interested from 10 to the power 3 to 10 to the power 6, because from 10 to the power 3 to 10 to the power 6 we do have to consider the effect of fatigue. From 1 cycle to the 10 to the power 3, that is 1000 cycle, the effect of the fatigue is neglected, and this region will be considered as a static failure region. Afterward we have fatigue failure region. So for any number of cycles between 1 to 1000, analysis is based on the static failure, and above 10 to the power 3, the analysis is based on the fatigue failure. So this time we'll use the fatigue failure for any number of cycle that will exceed than 1000. This figure represents the SN diagram for heat treated alloy steel, that is represented by core A. Medium carbon steel is represented by B. Core C represent here aluminium, and the core D is a generalized core. For the core A here, the knee is formed at this point, so corresponding will be the endurance limit, that is 5 into 10 to the power 5 in the case of heat treated alloy. This value of endurance limit will exceed in the case of medium carbon steel, and we'll find here that the knee is formed. This time we have endurance limit is 1 into 10 to the power 6. As such, for aluminium there is no knee form here, and therefore there is no endurance limit. And in the case of material D here, we have endurance limit is same as equal to 1 into 10 to the power 6. So endurance limit value is not fixed, it is continuously variable value, depends upon the material we are using. So in the case of non-ferrous material like aluminium, which do not exhibit any endurance limit, for such material the number of cycle to failure should be reported for the given endurance strength. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.